Hello everyone, my name is Sharaswathy and my matrix number is 224524. Today I am going to do my presentation. Thermodynamics EMM 3226, first and second law of thermodynamics. Application to the refrigeration cycle is the topic I chose. And for the introduction, objective of these slides are to explain the first and second laws of thermodynamics. The importance of these are understanding these laws is crucial for engineering applications, particularly in engineering energy systems. Let's find out what is thermodynamics. Thermodynamics in physics is a branch that deals with heat, work, and temperature and their relation to energy, radiation, and physical properties of matter. Thermodynamics is a macroscopic science. This means that it deals with the bulk system and does not deal with the molecular constitution of matter. There are three systems in thermodynamics. First one is open system. The mass and energy both may be transferred between the system and surroundings. For example, a steam turbine. The second one is closed system. The transfer of energy takes place, but the transfer of mass doesn't take place. For example, refrigerator, compression of gas in the piston cylinder assembly. And the last one is isolated system. Cannot exchange energy and mass with its surrounding. The universe is considered an isolated system. Now let's go for first law of thermodynamics. The first law of thermodynamics relates to heat transfer, internal energy, and work done. Also known as the law of conservation of energy, states that energy can neither be created nor destroyed, but it can be changed from one form to another form. Let me explain a bit. According to this law, some heat given to the system is used to change the internal energy while the rest is used in doing work by the system, where delta Q is the heat given or lost, delta U is the change in internal energy, and W is the work done. Let's go through thermodynamic processes. A system undergoes a thermodynamic process when there is some energetic change within the system that is associated with changes in pressure, volume, and internal energy. There are four processes includes adiabatic process, isochoric process, isobaric process, and isothermal process. Let me explain these four processes. An adiabatic process, which during this process no heat is transferred to or from the system. In isothermals, the system temperature remains constant, while in isobaric, the system's pressure does not change and it remains constant. The last one is isochoric, an isochoric process during which the system's volume does not change. Let me move on to the second law of thermodynamics. The second law of thermodynamics states that any spontaneously occurring process will always lead to an escalation in entropy S of the universe. Entropy is a measure of the disorder of a system. In simple words, the law explains that an isolated system's entropy will never decrease over time. Let me briefly explain about this. The equation for the change in entropy delta S is Q over 3, where Q is the heat transfer and T is the absolute temperature. For a given physical process, the entropy of the system and the environment will remain constant if the process can be reversed. If the physical process is irreversible, the entropy of the system and the environment must be increased. The final entropy must be greater than the initial entropy. This is the diagram for the example. Let's see statements of law. Calvin Klein's statement, also known as the heat engine statement, states that it is impossible to devise a heat engine that takes heat from the hot reservoir and converts all the energy into useful external work without losing heat to the cold reservoir. For the above process to happen, a part of the input energy must be wasted in the environment. In other words, the thermal efficiency of a heat engine cannot be 100%. Derived from these statements, the thermal efficiency denoted as nth for any heat engine. It serves as a dimensionless metric for evaluating the performance of a heat engine utilizing thermal energy. It is important to note that nth can be achieved 100% efficiency only when there is no waste heat. QC is zero. The next statement of law is clausive statement, also known as the heat engine or the refrigerator statement, says that it is impossible to construct a system that takes heat from the cold reservoir at temperature low and moves it to the hot reservoir at temperature hot without external work. It is well established concept of physics that heat moves spontaneously from higher potential to low and the reverse is not possible without some external work done. The first statement, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between same two thermal reservoirs. Second statement states that the efficiencies of all reversible heat engines operating between the same two thermal reservoirs are the same. The mathematical expression for Carnot cycle's maximum efficiency is N equals to 1 minus T cold over T hot, where T is the temperature, N is the efficiency of Carnot cycle. Tc is the absolute temperature in Kelvin of the cold reservoir, and Th is the absolute temperature Kelvin of the hot reservoir. Gibbs free energy. Gibbs free energy is the quantity that is used to measure the maximum amount of work done in a thermodynamic system when the temperature and pressure are kept constant. Delta G equals to delta H minus T delta S, where G is Gibbs free energy, H is enthalpy, T is temperature, and S is entropy. Let's move on to the main part of these slides. Application of first and second law of thermodynamics in complex engineering system. The example I chose was refrigeration cycle. Let's see the overview of refrigeration cycle. The refrigeration cycle is a thermodynamic process used to transfer heat from a low temperature reservoir to a high temperature reservoir. Key components in the refrigeration cycle is compressor, which increases the pressure and temperature of the refrigerant, condenser, which removes heat from the refrigerant, causing it to condense into a liquid. The expansion valve used to reduce the pressure of the refrigerant and cooling it down. And lastly, the evaporator absorbs heat from the environment, allowing the refrigerant to evaporate back into gas. Let's see cycle process. Compression. Refrigerant gas is compressed, raising its pressure and temperature. Next, condensation. The hot gas releases heat as it condenses into a liquid. And in the expansion, the liquid refrigerant expands, causing a drop in pressure and temperature. And the evaporation process is the cold refrigerant absorbs heat from the surroundings and evaporating back into gas. This is the overview diagram of refrigeration cycle. From compressor to condenser, expansion device, and the evaporator. First, I want to explain the first law of thermodynamics in energy conservation in the refrigeration cycle. Energy transformation. The first law of thermodynamics states that energy is conserved throughout the refrigeration cycles. Let's see the process breakdown. In compression stage, work is done on refrigerant, increasing its internal energy, and input equals to work done on refrigerant. In condensation stage, heat is released to the environment as the refrigerant transitions from gas to liquid. Energy output equals to heat released. In expansion stage, the refrigerant undergoes an expansion, dropping in pressure and temperature without heat exchange with surroundings. And lastly, in the evaporation stage, heat is absorbed from the environment as the refrigerant evaporates, converting back into the gas. Energy input equals to heat absorbed. Each stage demonstrates how energy is conserved and transformed adhering to the first law. And for the second law of thermodynamics in refrigeration cycle, entropy change in the refrigerant cycle. Entropy concept. The second law of thermodynamics states that total entropy in an isolated system can never decrease. It either increases or remains constant. Entropy analysis in refrigeration cycle. During each stage of the cycle, entropy changes occur due to irreversible process. Compression stage. Work input increases internal energy but also contributes to entropy due to friction and inefficiencies. Condensation stage. Heat rejection increases entropy in the surroundings while decreasing entropy in the refrigeration. In the expansion stage, rapid expansion leads to an increase in entropy as pressure drops quickly without heat exchange. And lastly, in the evaporation stage, absorption of heat increases entropy in the refrigerant as it transitions from liquid to gas. The overall impact is the refrigeration cycle demonstrates how work must be done against nature entropy flaw, highlighting inefficiencies and energy losses. What are the complex interactions in engineering systems? First, technical challenges. Engineers must balance efficiency with energy consumption. Improving system efficiency often increases initial cost or complexity. Non-technical factors. Considerations include environment regulations, societal impacts, and economic factors that influence design choices. Trade-off example. Increasing insulation can reduce energy loss, improving the efficiency, but may increase material cost and impact sustainability. These are the complex interactions engineering face in the engineering systems. In the refrigeration cycle, this is how the transfer of heat happens. And this is the graph or diagram for entropy change illustration in refrigeration cycle. We take some different refrigerants and compare its performance curves. This is the entropy change illustration in refrigeration cycle. I mean in different refrigeration cycle. In conclusion, the first and second laws of thermodynamics are foundational in understanding energy systems. Their application in refrigeration cycles highlights critical interactions between energy conservation and entropy changes. These are the references I used to prepare these slides and presentation. Thank you.